What if every electron in the universe is actually the same electron? Not similar, not identical, not copies of some perfect cosmic template. The same particle, an electron inside your body, an electron racing through the sun, an electron trapped in a laboratory on Earth, an electron that helped create the first stars billions of years ago. What if somehow all of them are really one and the same object, appearing again and again at different places in different moments in space-time? It sounds like science fiction. It sounds impossible. And yet this strange idea has appeared in serious discussions about the foundations of physics. The story begins with something that seems almost too ordinary to be interesting. Every electron has exactly the same mass, exactly the same electric charge, exactly the same spin, exactly the same magnetic behavior. As far as modern experiments can tell, there is no such thing as a slightly different electron. Nature does not give us a catalog of electron models. There is just the electron. That fact is so familiar to physicists that we rarely stop to ask what it actually means. Imagine walking into a room filled with 1,000,000 identical coins. You could still distinguish one coin from another. You could put a tiny mark on each one and follow its journey. Even if they were manufactured to exactly the same specifications, they would remain individual objects. But electrons are different. In quantum mechanics, two electrons are not merely difficult to distinguish. Fundamentally, they are indistinguishable. If you exchange two electrons, the laws of physics do not give you a new physical situation that can be detected. The particles are described collectively, and for identical fermions like electrons, their quantum state obeys a very specific anti-symmetry rule. This is not just a statement about our imperfect ability to observe them. It is built into the mathematical structure of quantum theory, and this is where the mystery begins. Because if two electrons are fundamentally indistinguishable, what exactly makes them two different electrons? Leonard Susskind has spent much of his career asking questions that live precisely at this boundary between what our everyday intuition tells us and what the laws of physics actually permit. Susskind, one of the major figures in modern theoretical physics, helped develop ideas surrounding string theory and played a central role in the modern understanding of black holes, quantum information, and the holographic principle. His work repeatedly leads to the same unsettling lesson: reality may not be organized according to the categories our brains naturally prefer. We imagine the universe as a collection of things, objects, particles, stars, planets, people. We picture each thing as possessing an identity that remains attached to it as it moves through time. But quantum mechanics begins dismantling that picture. At the smallest scales, nature does not necessarily behave like a universe filled with tiny billiard balls. Instead, quantum theory describes states, probabilities, fields, interactions, and information. And in modern quantum field theory, the electron becomes even stranger. The electron is not fundamentally understood as a tiny solid sphere moving through empty space. It is an excitation of an underlying quantum field. There is an electron field extending throughout space. What we call an electron is a localized excitation of that field. This is a profound shift in perspective. Think about the surface of an ocean. You can point to one wave and say, that is a wave. But the wave is not a separate substance from the ocean. It is a pattern moving through something more fundamental. If another wave appears several kilometers away, you don't necessarily have two different kinds of things. You have two excitations of the same underlying medium. Quantum fields are not literally oceans, and this analogy has limits. But it helps reveal the basic idea. An electron here and an electron there are not two different species of object. They are excitations of the same electron field. This helps explain why every electron has the same fundamental properties. But it also raises a deeper question. Could the phrase "this electron and that electron" be fundamentally meaningless? Suppose an electron travels from point A to point B. Then another electron travels from point C to point D. Classically, we would naturally imagine two separate histories. Electron number 1 followed one path. Electron number 2 followed another. But quantum mechanics does not always allow us to assign such definite individual histories. When identical quantum particles interact, the mathematical description must account for the fact that exchanging them does not create an observable distinction. The universe doesn't carry little name tags saying electron 1, electron 2, electron 3. Instead, the quantum state describes a system of indistinguishable particles, And this is where one of the strangest ideas in the history of physics enters the story. It is sometimes associated with physicist John Wheeler, who imagined a universe containing only one electron. The basic thought experiment was extraordinary. Perhaps there is only one electron in the entire universe. It travels forward and backward through space-time. Every electron we observe could be a different appearance of that same underlying object. Wheeler reportedly proposed the idea during a conversation with Richard Feynman, who later recalled it in a famous anecdote. The thought experiment was never established as a description of reality. It was an imaginative way of confronting the strange behavior of electrons and the possibility that antimatter could be interpreted through particles moving backward in time. But there was a problem. If the universe contained only one electron, why do we observe vastly more electrons than positrons? We see enormous numbers of electrons. Atoms contain them. Stars contain them. Matter throughout the universe contains them. Yet the universe does not appear to contain equal numbers of ordinary electrons and positrons in the way the one-electron picture would naively suggest. So the one-electron universe is not accepted physics. But the question it exposes remains incredibly important. Why are all electrons exactly alike? And what does individual particle actually mean in a quantum universe? To understand why this matters, we need to step away from electrons for a moment. Consider two photons. If two identical photons meet, quantum mechanics does not give us a meaningful physical label that says which photon is which. You might imagine one photon as having a little identity card. But nature does not appear to provide one. Now consider two electrons. Because electrons are fermions, their quantum states obey the Pauli exclusion principle. This principle is responsible for something astonishingly important. The structure of ordinary matter. Why don't all electrons collapse into the lowest possible energy state inside an atom? Because identical fermions cannot occupy the same quantum state. That simple rule helps create the structure of atoms. It determines how electrons fill atomic orbitals. It shapes chemistry. It helps determine why matter occupies space instead of simply collapsing into an undifferentiated quantum pile. The chair you're sitting on, the screen you're watching, the atoms in your hands, all of this depends on the quantum behavior of indistinguishable particles. So the mysterious sameness of electrons is not a philosophical curiosity sitting at the edge of physics. It is woven into the structure of the world around you. But Leonard Suskind's work takes us toward an even more unsettling possibility. What if particles themselves are not the deepest layer of reality? For most of modern physics, the hierarchy seems straightforward. You break matter into molecules, molecules into atoms, atoms into electrons and nuclei, nuclei into protons and neutrons into quarks. Eventually, perhaps, you might imagine arriving at the smallest ingredients of reality. But theoretical physics has increasingly challenged this simple picture. In quantum field theory, particles are excitations of fields. In string theory, the fundamental entities are described differently still, tiny one-dimensional objects whose vibrational states can correspond to different particles. An electron would not simply be a tiny bead. It would emerge as a particular quantum state of a more fundamental object. And Susskind has been deeply involved in the broader theoretical landscape where questions like this become unavoidable. String theory attempts to describe particles and forces within a unified framework, while also confronting gravity at the quantum level. The central idea is radically simple to state. What appears to us as different particles may correspond to different states of something deeper, different vibrations, different excitations, different patterns. Imagine a violin string. One physical string can vibrate in many different ways. One mode produces one frequency, another produces another. The string has not become a different object. Its state has changed. String theory extends this kind of idea into a far more sophisticated mathematical framework. Different vibrational states can correspond to different particles. The analogy is imperfect, but the conceptual message is powerful. Perhaps nature does not begin with thousands of fundamentally different building blocks. Perhaps many things we perceive as distinct are different manifestations of a deeper underlying structure. And then black holes enter the story. This is where Suskind's work becomes especially relevant. For decades, black holes seem to create a terrifying conflict between gravity and quantum mechanics. General relativity says that matter collapsing beyond a certain point can create a region from which nothing can escape. Quantum mechanics says that information about a physical system cannot simply disappear without consequence. Then Stephen Hawking discovered that black holes are not completely black. They can emit thermal radiation, and this created what became known as the black hole information problem. If a black hole forms from matter carrying an enormous amount of information, and the black hole eventually evaporates into apparently thermal radiation, what happened to the information? Was it destroyed? If so, one of the deepest principles of quantum mechanics would be threatened. Or is the information somehow preserved? Susskind became one of the leading voices arguing that black hole physics should preserve quantum information. The debate eventually transformed our understanding of gravity itself. And one of the most astonishing ideas to emerge from this revolution was the holographic principle. The basic intuition is breathtaking. The information describing a volume of space may, under certain circumstances, be encoded on a lower dimensional boundary. Reality might contain far less independent information than our everyday experience suggests. A three-dimensional world could, in some profound sense, be describable by information living on a two-dimensional surface. Susskind and Gerard G. Hooft were among the physicists who developed this idea in connection with black holes, and Susskind later helped develop its relationship to string theory through holographic dualities. Now consider what this does to our original question. If particles are excitations of fields, if quantum states are fundamentally about information, if space-time itself may have a deeper description, then perhaps asking whether two electrons are truly separate objects is already asking the wrong question. Maybe the universe doesn't fundamentally contain electron number 1 and electron number 2. Maybe it contains a quantum field, a mathematical structure, and particular excitations of that structure. The distinction between particles could be something that emerges from the state of the system rather than something fundamentally attached to each particle. This is one reason quantum field theory feels so different from classical physics. In classical physics, you can imagine following an object. A baseball leaves your hand. You can track its position at every moment. You can imagine that it possesses an identity continuously through time. But quantum theory forces us to be more careful. At microscopic scales, what we call a particle is deeply connected to the entire quantum state. And in relativistic quantum field theory, particles can even be created and destroyed. An electron and positron can annihilate. Energy can be converted into particle excitations. Particle number itself is not always a fixed fundamental quantity. The deeper entity is the field. So perhaps the question is no longer which electron is which. Perhaps the better question is, what is the quantum state doing? This may sound like a technical distinction. It isn't. It changes the picture of reality. Imagine you have a stadium filled with identical waves moving across a giant electronic display. You could point to one bright spot and call it wave number 1. But if the pattern changes, the identity of that spot may become impossible to define. The fundamental reality is not the individual bright spot, it is the entire pattern. Quantum physics can behave in a surprisingly similar conceptual way. And this brings us back to the provocative title of our story. Could every electron be the same one? The scientifically responsible answer is we have no evidence that the universe literally contains one electron moving through all of space-time. That is not the accepted theory. Modern quantum field theory does not require a single electron. It describes electrons as excitations of the electron field, and multiple electrons can exist simultaneously as parts of a many-particle quantum state. The one electron idea is therefore best understood as a thought experiment, not a discovered fact. But something even stranger is true. Every electron really is fundamentally identical to every other electron, not because we haven't found their differences yet. According to our best theories, there are no hidden individual identities of the classical kind. And this sameness is so exact that it becomes one of the most reliable features of modern physics. If you take an electron from a distant galaxy and compare its intrinsic properties with an electron in a laboratory on Earth, our theories say they are the same kind of quantum excitation. The universe does not manufacture slightly different electrons. It gives us one electron field, and that field can be excited again and again. Now imagine taking this idea to its philosophical extreme. Your body contains electrons. Those electrons were not created specifically for you. They have existed in the physical history of the universe as parts of countless interactions. The atoms in your body were assembled from material forged through cosmic history. Some of the matter around you has passed through stars. Some of the particles that now participate in your biology once belonged to other physical systems. You are not made from special cosmic ingredients. You are made from ordinary matter, obeying extraordinarily strange laws. And if quantum field theory is telling us something profound, perhaps individuality itself is not written into the smallest layers of reality. At the macroscopic scale, you are obviously an individual. You have memories, a history, a location, a body, a perspective. But descend far enough into physics, and the universe becomes less interested in labels. There are fields, there are quantum states, there are interactions, there is information. There are patterns that persist long enough for us to call them objects, and perhaps this is why Susskind's work is so philosophically unsettling. His research does not tell us that reality is an illusion. It tells us something more subtle. Reality may be real while being radically different from the picture our intuition gives us. We evolved to understand rocks, trees, predators, rivers, and other human beings. Our brains were not designed to intuit quantum field theory. So when we ask, where is the electron, or which electron is this, we are importing everyday concepts into a domain where those concepts may no longer apply. The electron doesn't need a tiny identity card. It doesn't need a unique personality. It doesn't need to remember where it was yesterday. The mathematics of the theory already tells us what matters. Its quantum state, its interactions, its measurable properties, its place within the larger system. And perhaps this is why the idea of one electron haunting the entire universe remains so memorable. It forces us to confront something we normally ignore. The universe may not be a collection of separate things. It may be a single interconnected quantum structure whose excitations appear to us as separate objects. That does not mean everything is literally one particle. It means that the deepest description of nature may not be organized around the boundaries we see. The stars look separate. Planets look separate. You look separate from the screen in front of you. But at a deeper level, all of these things are manifestations of fields and quantum states governed by the same underlying laws. And the same laws apply everywhere. The electron in your hand does not know that it belongs to Earth. An electron near a distant black hole does not receive a different version of physics. There is one set of laws, one electron field, one quantum framework, and perhaps one universe whose apparent multiplicity emerges from patterns within something deeper. The most haunting possibility is not that every electron is literally the same electron. It is that the question of whether they are different may have no fundamental meaning at all. Maybe individuality is an emergent feature. Maybe one and many are concepts that become useful only after the universe has organized itself into recognizable patterns. And if that is true for electrons, we have to wonder how far the idea extends. If the objects we call particles are excitations, if space-time itself may emerge from deeper quantum information, if black holes can force us to rethink where information lives, then what exactly is the universe made of before we divide it into things? Perhaps the deepest layer of reality contains no particles at all. Perhaps it contains only relationships, patterns, information, quantum possibilities. And from those possibilities, everything we recognize as separate may emerge, including you. So the next time you look at an electron as a tiny point of matter, remember the strange possibility hidden beneath that simple picture. There may be no this electron and that electron in the way we imagine. There may only be one underlying quantum reality, expressing itself in countless ways. And if the universe does not fundamentally distinguish one electron from another, then perhaps the oldest question in physics is not why every electron is the same. Perhaps it is this: if individuality disappears when we look deeply enough into reality, where does the boundary between one thing and another actually begin?